Greetings, welcome back ladies and gents. Double summation for today. We're going to look at something which at first glance it looks fairly scary looking. A double sigma notation if you want, and the summand or the bit inside the summation is 1 over 3 to the power of m plus n. So first of all, how do we do something like that? Is it difficult is another question. The answer is the first time you see this, it does look quite daunting, but it's not actually. This particular one is not hard at all. Let me just first of all put a bracket, okay, because there should really be each sigma should have its own argument. So that's the argument of the outer sigma, so that we're gonna sum things which look like this, but of course the inner sigma should also have another argument if you want, and this is what's inside the second sigma. So how do we do something like this? We treat it a little bit like integration, those who have seen integration to variables. So it's actually, we approach it as follows. Step by step, I'm just merely copying it at the moment. I'm going to use the brackets that I've just introduced in there. And sigma again, from m is equal to 0, and try to make sense of it. The only thing I can think of doing at the moment is to split the denominator of this fraction using the rules of indices to 3 to the m times 3 to the n. Close this argument here and close the outer argument. Okay, what do we go next? Now, you know when you have integration, and I'm using integration because summation and integration are kind of very much related. Suppose you had something which looks like this. 1 over 3 to the m times 3 to the n, and your integration. Actually, let's use different variables. Let's say we're having x and y's because we're not likely to having m and n in integration. 3 to the x times 3 to the y, and the integration, it was with respect to x, let's say. So we could actually write this on the next line as 1 over 3 to the x times 1 over 3 to the y, still dx. Now it's fair to say, if I had an integration, this particular term, which is independent of x and is part of a product, I could factor it out and write definitely that's the same as 1 over 3 to the y integral of 1 over 3 to the x dx, because as far as this integration is concerned, which with respect to x, this is a constant. So a similar thing happens with summations in there. So let's look at the inner, if you want, summation. Let's split that as we just done with the integral. So sigma, I don't know if it's a good idea to carry on writing these brackets. It's probably more confusing than they're actually helping, but let's leave them in there. Okay, that's the inner sigma now, and all I'm doing is, as I've done in the integral, I wrote this as 3 to the m times 1 over 3 to the n. And this is what I've done so far. And let's look now at this particular sigma. This sigma is running in m. That's like on the integral it was with respect to x, the dx. So anything that has n and is in a multiplicative form is actually independent of the summation, and I can pull it to the front. Think of it in sigma notation. Of course, if you have something a to the r squared, and you have, of course, the summation is in r, it doesn't matter what's on the top, this a can go on the outside. It's independent of r. Okay, so it's the same idea here. So I'm gonna get out of the way in a second, so just bear with me. N is equal to 0 to infinity, and this is summation in m. The n I'm gonna pull outside, so it's going to be 1 over, oops, I wrote it wrong, should be 3 to the n from there. So this bit I pulled outside, still have the other sigma, which is running in m, to infinity, 1 over 3 to the m. And that, of course, is the argument, if you want, of this sigma. And all of this now is the argument of the outer sigma. can I do this one here? So I'm just concentrating on the inner sigma. What does that actually say? Let's look at it. It says 1 over 3 to the 0. So I'm just looking at this by putting m is equal to 0, plus 1 over 3 to the 1, plus 1 over 3 squared, plus dot dot dot. So that's 1 plus a third plus a ninth plus dot dot dot, which of course is a geometric progression, a GP, with first term is equal to 1 and a common ratio of a third. And of course we sum it from naught to infinity. So that's the sum to infinity. And of course the formula for a sum to infinity for a geometric progression is a over 1 minus r. So in this particular case it will be 1. And we should get something nice and simple. 1 divided by 1 take away a third is 2/3. So the answer is 3 over 2. So this particular, let me just put it in green. I don't know if you followed what I've done in there. I hope you did. This quantity, let me just move the mic out of the way, is actually turning out to be 3 over 2. This is, of course, all of that forever, which we wrote it explicitly, geometric progression, blah, 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 sum to infinity. So my next line now for all of this will be that is equal to sigma, that's now running in n is equal to 0 to infinity. I've got the 1 over 3 to the power of n still in there. Let me clear some of this stuff out to make some space. And all of this turned out to be 3 over 2. So now we lost one of the sigmas in all of this. So that looks a little bit better now. And I think now even students in year 12, I don't know when you do geometric progressions anymore, at A level, you should be able to tackle this. This is a constant, okay? We can't pull it in front of the sigma. We could also cancel that, but it doesn't really matter. Probably the best thing is to put the 3 over 2 on the outside, as it has no n dependence. And this will now become n is equal to 0 to infinity. And of course, I've got 1 over 3 to the n, which I hope it doesn't bother you, because earlier on we done it in m. It will hardly matter. That is still the same. It's still 1 over 3 to the 0 when n is equal to 0, plus 1 over 3 to the 1, plus 1 over 3 squared, plus dot 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 forever. We've done that sum to infinity. It will in fact equal to 3 over 2. So again, this particular sum is just another geometric progression with a sum to infinity 3 over 2. And of course, the final answer to our problem, all of this mess up here, is in fact 3 over 2 times 3 over 2, which is 9/4. So I don't think it was bad at all. I think it was quite okay. I hope you follow what I've done. And who's laughing now? Join me again.